examples of computing normal ordering. So, I'm going to do example A. Right. So, so I have a normal order of del of x mu of z. Okay. Del bar. Actually, I'm just going to do a holomorphic class. So actually here, when I write down del x mu, then I do mean that it depends only on z. It doesn't depend on z bar, okay? Because it's a holomorphic according to equations of motion. Then I have something like this, and this guy is del prime of x mu of z prime, and then I have del prime of x mu of z prime. Okay, so so at this stage it looked funny. Why in the world would I look at this operator? And so I want to write it down as a normal ordering, or if you wish, you will see that doing normal ordering here is going to extract for us the singularity. The reason why we will be interested later, because this guy is going to be a stress energy. This will be related to a stress energy tensor, two-dimensional CFT. So I haven't introduced it, but I will just say related to stress energy tensor. And so what is happening is that I'm asking the question, what is the singularity structure when I look at the product of two stress energy tensors in the CFT? And there will be a lot of information about conformal theories encoded in this OP. But we're going to compute this just in a free field series way how we derive our contractions. Okay, so according to this rule, what I have to do, I have to write it down as I guess I have to write it down completely. X mu, del of x mu, del of x mu, del of x mu. So those, there is a normal ordering here, and so actually, this operator doesn't have any singularity. So because there is a normal ordering, so this guy depends on that. This guy depends on that prime. But there are no singularities in this product. Because of the normal ordering, it satisfies the equation of motion like a classical equation of motion. Okay? No singularities. So, is it clear? Because I can act with with del bar and show that that actually vanishes, and so it must be a holomorphic function which must have a well-defined Taylor series extension. Okay, and then there are cross contractions. So when I do exponential, so I have four fields. So only the first two terms in the expansion of the exponential will contribute. So let's look at the first one. So the first one is going to be minus alpha prime divided by 2. Okay, and so now one of the fields must act on the first operator. So this is my F operator. This is my G operator. But each of these operators involve two fields. So altogether there is a symmetry factor of 4. Right? I can choose whether this del over del xm acts on the first or the second one. So if I act it once, then one of the operators, one of the x's removed from here, one of the x's will be removed from there, and so I will be left with del x mu of x, del x mu, sorry, del x mu of z, del x mu of z prime. There will be a normal ordering here, right? And then I removed removed one of the x from f, one of the x from g, and so I will have log of z minus z prime squared times, right, so every time I remove, I insert this log, and that would be the case if there wouldn't be any derivatives, but now I have derivatives, so those derivatives will act on this log function, and so I will have del over del prime acted on a log function. So this is the first piece. Okay, so any questions? What's the first one? Good. So, and after that, there will be one more term when I expand the exponential of this functional derivatives. So there will be additional term. So it's going to be equal plus 1 over 2 factorial, right? And then I have minus alpha prime over 2 squared, right? So I have to take a square of that. Actually here, once I do that, then there will be eta mu. Right? So I remove one of the x with index mu, one of the x with index mu, so there is eta mu there. Which is important because that precisely will allow me the proper contraction of indices here. Right. So so once I do that, so now I have 4 x's, 2 derivatives acting on the first one and 2 derivatives acting on the second one. So I claim that the symmetry factor is still 4, and the reason for that is that in order to choose how the first derivative acts, you have a 4-fold degeneracy, right? So there is a factor of 4. But once you choose how the first derivative acts, the second derivative has no choice, right? That's what I'm saying. So there is a factor of 4 when they acted once, and this was from F, this one was from G. So the second one acts only in a single possible way. So the symmetry factor of the second guy is the same. And then I would have eta mu, so there will be 2 eta mu's because there will be two pairs of derivatives. And then I have del over del prime log z minus z prime squared. Okay. And nothing else, okay, plus 0. So what we did, we actually computed exactly what the normal ordering product here is. The reason is that at this stage, there are no x's left. And so if I continue this expansion has an infinite set of derivatives, but I cannot act with more than 4x derivatives, right? Because I have only 4 x's in my operator. Okay, so now I can use the arithmetic, and I will find out that this is del mu x, del mu x, del prime x mu, del prime x mu, normal order. Right? And then there will be a singular part, and so the singular part is going to be equal alpha prime squared. I will start writing down the most singular piece. So here I have a contraction of eta mu, so that gives me how many scalars in the worldsheet I have. So this is D, right? And then now the coefficient is, so I have one half left. So there will be a factor of 2. So now I have to act with del prime, and I have to act with it many times. And if you do it carefully, you will find out that here is z minus z prime to the fourth power. Actually, it's easy. That's only one, so you will have 1 over z, the other one over z prime squared, and then you square it. It's the right answer. So it's a 4th order singularity, and then there is this piece here. So this guy has a factor of 2 because I have 4 divided by 2. This will be minus 2 alpha prime z minus z prime squared, and then I have a normal ordering of del x by the way, just running ahead, you can see that in a singularity structure, we have T times T, something related to a stress energy tensor. So we look at the product of TT and the singularity structure. This is an identity operator. Right? And then up here, what comes up is a stress energy tensor again. Exactly the same operator as we start. So that will be it will be a general picture, as you will see in a second. But for now, don't think about it. This is just an arithmetic in which we learn how to use this cross contraction. So are there any questions? Good. So next thing.
Can I ask a question not related to calculations?
Yep.
Is in this form, it seems that formally it looks very similar to the case when you're dealing with path integral quantization of interaction fields.
Yep.
Usually you factorize out the interacting part and replace those field quantities by functional derivative with respect to external fields, the source field, and then all the Feynman diagrams are generated by that function. But formally they look very similar.
Yes, and the reason is it's kind of similar, except that so what you said, you have a free field, and then you're extracting a piece which is interaction. So the way to think about this is, remember, the way to go from normal ordering, from a product of operators to normal ordering, is kind of stripping off quantum effects. So you can think of is that what this piece is doing, it encodes all the quantum corrections which can happen in this conformal theory. But it's not, we don't know yet that it is conformal in this two-dimensional field theory. So that's why it's more or less similar. Except that those are the pieces, they are the ones that correspond to quantum corrections. That what changes you. If everything would be classical, then the product, there would be no difference between normal order and standard product. Okay, which is exactly the same as it is if you think in a path integral, right? So if there would be no interactions, then there would not be this additional interacting Hamiltonian piece. It's a good observation. Right, so that was A. Now example B. So example B will be important when we study scattering amplitudes. And so all the vertex operators on the string worldsheet will have some nice form. And so what we need to do, we need to now, since we're practicing, practice with something useful. So let's practice with two operators. It turns out that those will be their vertex operators. Those will be the operators that you need to insert in the Polyakov action conformal field theory to compute the scattering of tachyons. Remember, in our bosonic string series, there are tachyons. How do we study the scattering of tachyons? I told you that in order to do that, we will need to study the correlation function, right? And we need to find out what operator corresponds to tachyon. So we'll find out later that that's an operator to a tachyon, which moves with momentum k1, right? So what I mean here, this is just k mu x mu, right? So this is an external space, and then there is g is e to the I k2 x of that prime off, okay? So again, it's just a word for you now, but you will learn later that those are tachyon operators corresponding to tachyons. Okay, so those are the tachyon vertices, and by studying the correlation functions of this operator, I can ask the question, how does my tachyon scatter in string theory, compute various scattering amplitudes? So for our example, what we want to do, we want to compute this normal ordering so strictly speaking, what I'm assuming that there is a normal ordering here. Okay. actually, that's a trivial statement because I didn't have to do it. Remember, the normal ordering of the field is the field itself, and so as long as all the fields are at the same point, I can exponentiate them. Good. So I can use the general formula. So the general formula tells me that this is exponential minus alpha prime divided by 2. And then I have this d2 z1, d2 z2, log absolute value z1 z2. And then now I have delta over delta x f, delta over delta x g. Okay, acted on the ik1 x, the ik2 x. Okay. So actually, we can compute this exactly, even though it seems a little bit complicated. And the reason is, that when let's look what this guy is, right? So if I have with delta x of e to the ikx, what will I get? Right? So I will get e to the ikx, what I had before, and then I have to differentiate ikx with respect to x. So if I have x mu here, then it will be iku, right? And then if there is a difference, for example, this is z2 and this is z1, then I will have a delta function of z1 minus z2. Okay? That's all what it is. So now it's clear that if I have these derivatives acted in exponential, the only thing that this guy is doing, it simply introduces this factor, I times momentum times the delta function. So then I can write down the next slide there. So that will be an exponential of minus alpha prime over 2. The integral, so I will have 2z integrals. Well, let me do it slowly. So I will have an integral d2z1, d2z2. Okay, and then I have log z1 2 squared, right? Now each of these will bring a delta function and will bring ik. So I will have ik1 mu, right, times the delta function. So the first one, this guy is at 1, this guy is at 2, and so this will give delta function z1 minus z2. And then the other one gives me ik2 mu, right? But actually the indices are contracted, right? There is mu here and there is mu down there. So k1 mu, k2 mu, then I have delta 2 of z2 minus z2 prime, okay? And so this exponential is just a factor that goes in front. So now here I have e to the ik1 x of z, e to the ik2 x of z prime. Okay, so is that clear? So now you can see that the delta functions will cancel, right? So against the integrations. And the only thing is the delta function will do, it will simply tell the log argument what that one is and what that two is. So what we are finding is that normal ordering f, normal ordering g equals e to the alpha prime over 2. And then I have I times I simply going to give me K1. Well, I will have simply a dot product of K1 times K2. I squared will cancel against -1. And then the delta functions will simply tell me that I have log that minus that prime squared. Right? And the normal ordering. Okay, so what this tells me that I can actually exponentiate this, and so this is going to be equal z minus z prime to the power of alpha prime K1 times K2. Okay. Right. So I guess well, I want to. No, I don't want to go into details. Okay. So any questions, guys? So we have two examples, and we showed exactly how we do contractions or compute the normal ordering. And in both examples, we computed the normal ordering exactly. Okay, so we didn't make any approximation. So those are exact quantum mechanical statements. All right, so very good. So now we change the gears. What we're going to do, we're going to talk about word identities, and we're going to talk about derivation of word identities from the path integral formulation. And the reason we're going to do that is because by studying that, we will discover conformal symmetry in this scale diffusive. We will discover a lot of additional symmetries hidden.
I was just wondering why we would ever really care about a normal order product.
Right, very good question. So I told you that what we do here is not as much as about normal order, but about the correlation function. So the expectation value of the normal order will be 0 always. Okay, so which means that if we have this normal ordering, so for example, so I didn't want to talk about it, but since you asked, so let's look at, suppose I have one insertion at Z, okay, and another insertion is so K1, K2. X of 0, right? So what this tells me that this is, so what they did, I simply choose that prime to be 0. Okay? So then this is Z, and to the power alpha prime K1, K2, and then here I have normal ordering e to the I K1 x of Z, and then e to the I K2. Right? So now the point is that this is a normal ordering, which means that it's a nice holomorphic. It satisfies a classical configuration. So what this means that I can do a Taylor series expansion here, right? So when I do a Taylor series expansion, so this guy is going to be 1 plus some terms which are ordered ZZ bar. Right? Now there is a normal ordering. So if I do this normal ordering of these guys will vanish. Okay, those are some non-trivial operators. It's only the identities that will survive. So the whole point is that what we are doing, we have operators inserted at different points, but we replace them in the full set of all operators in the CFT, the basis set. One of those basic operators will be an identity operator, something that you see explicitly here. Right, so we do when we do this OPEs, so what they did operator product expansion here. So there is an identity plus other guy. So the other guy will not contribute to correlation function. And so the correlation function will be governed by this expansion. Okay, so that's, if you wish, by studying OPEs, we study techniques that will be useful to compute correlation functions later. And actually, that piece will eventually lead us to scattering amplitude, and we discover Virasoro amplitudes, which were guessed at the very beginning of string theory. That's how the string theory started. people didn't, people understood much later the root association. All right, so, but for now, you shouldn't be asking these good physics questions. What you have to think of this is that we're going to study this for the sake of it. So we decided that this two-dimensional conformal field theory is a beautiful, this two-dimensional field theory is a beautiful, beautiful example to study, and we are theoretical physicists, so we're just going to do it, okay, without any reason. Good. So what I'm going to discuss now, what are they doing? And so I'll try to be very, very careful, and I try not to forget signs. They're important and they're confusing. So it's word identities plus Neosov series. Okay, so you have seen this before, but I'm going to repeat it again anyway. So suppose I have some field, okay? So some field alpha, and there is a transformation. Phi goes to phi prime, and so I can write it down for infinitesimal transformations as what I had before, plus epsilon times delta phi alpha of sigma. Okay? So I'm going to assume that this transformation is my exact symmetry. Okay, so this is exact symmetry. Exact symmetry of my quantum field theory. So this epsilon is infinitesimal parameter of the symmetry transformation, right? So infinitesimal. Okay, so I'm going to now destroy this exact symmetry. The way how I'm going to destroy, so it's important that I'm talking about global symmetries, meaning that del A of epsilon equals to 0. Okay, so it's a symmetry. It's a symmetry which is independent on the bullshit coordinates. Okay, of multidimensional field theory. And so now I'm going to ask the question, what are the implications if instead of making symmetry transformation with constant parameters, I will make parameters which depend on coordinates. So I will make, in some sense, what I'm doing, I'm engaging this global symmetry transformation. So in other words, I'm going to study what will happen when phi will go to phi prime, okay, which is the same as phi alpha plus epsilon times rho of sigma times delta phi alpha. Okay, so what I did, I inserted explicitly some non-trivial function. I'm going to assume that this rho of sigma has a finite support, which pretty much means that it's 1 or non-zero in a small region and it's 0 outside. So I want to know how does my path integral transform, right? So by the way, when I talk about exact symmetry, I mean symmetry including both transformations in the measure and in the e to the minus x. So it's important that sometimes there can be anomalies associated with transformations of the measure. So what I did, I just wrote path integral in terms of this phi prime variable, right? And so I want to know how is it expressed to linear order in epsilon. And so I'm going to make a statement that this is d phi. I'm just going to, if you wish, this is a definition. So I'm going to. Well, I know that there will be some transformation, but at the end of the day, it must be of this form. So del phi e to the minus s. And here, I'm going to write it down. as 1 plus I epsilon over 2 pi. Okay, bear with me. Those are the conventions that will be useful for us. So we have to stick with that. And then here I have d2 sigma. So I switch to sigma 1, sigma 2 coordinates. It doesn't matter. Actually, I can do it in general. Square root of minus g is a metric. And then there is a, I'm going to write it down as JA, okay, of sigma times del A of rho. Okay, so this is an integral, right? So I inserted square root, so this is an invariant volume measure, right, or area measure in this case. And then I have JA times the rho, and then plus higher order in action correction. So all I said is that you tell me there is some symmetry transformation, and I'm saying that if you have that, then the path integral will change. And I ask how is the change what would be the change in this path integral? And all I'm saying is that it will be 1 first, right? And then there will be order epsilon correction. And all I'm saying is that this order epsilon correction must depend only on the derivative of rho. Okay? The reason for that is that if rho is constant, then it's an exact symmetry. So meaning that all these guys must vanish. So these corrections from 1 will come only containing derivatives of rho. Is that clear? Okay. Okay. Very good. But now, and again, we just look at the leading product. But now I'm going to make a statement that an integral of d phi prime e to the minus s of phi prime is the same as the integral of d phi e to the minus s of phi. Okay? And the reason for that is that all I did in this line, I just changed variable. Okay? I don't care if it is symmetry or it's not symmetry. All I need to do is that you told me that there is a relation between phi and phi prime, and so all I did, I just transformed. So this is a change of variables in the path integral. Okay, so this is change of variables. And actually, it's not even an interesting change of variables. It's something of the type, when I have an integral dx 1 plus x, I can write it down as an integral of dz 1 plus x. Okay? It's just a relabeling what is my variable of integration. So that's all what is happening. However, that trivial manipulation tells us that I can look at that identity, right? And so now I will have 0. What I'm doing, I'm going to take this side and I'm going to subtract the side here. Okay? So you can see, and I'm going to keep only terms to linear order epsilon. So there will be an exact cancellation of these two pieces. Okay. So first of all, the answer. All I'm doing, I'm pulling this one on this side and using this identity, and so that's this 0, right? So this is an integral of time minus an integral without the time. And so what I will be left, I will be left with I epsilon over 2 pi, and then the functional integral of d phi e to the minus s, right? I want to do it now. Let me see. Yeah, I'm going to do it now. So I'm just gonna integrate. Okay, sorry. What I did. Okay, no, it's not what I want. I want actually to move all of these guys on the other side. So I will have 0 still, right? But I will have a minus sign here. Okay. will have a minus sign, so I have pi epsilon over 2 pi, this functional integral, and then I have, which is not a big. The sign will be important later. That's why I struggle with the minus sign a lot, so I want to keep careful. So then there is d2 sigma, and then I have square root of minus g, and then I have, I integrate by parts. So, well, let's do it first. So then I have JA del A of rho. Okay? So what I can do, I can now integrate by parts. And so inside this integral, and so when I integrate by parts, there will be a sign flip, and it's important, if you want to be careful, it's important to plot as a finite support, which means that I don't have to worry about the boundary term. So then it becomes plus pi epsilon over 2 pi, and then I have d phi e to the minus s, and then I have an integral of d2 sigma square root of minus g, and then I have nabla a g a times 1. Okay, so x equal to 0. So what did we derive with u right now? Well, I'm going to write it down in the following form. So I need 2 more lines. So 0 equal minus epsilon over 2 pi. I'm just following my notation. Minus epsilon over 2 pi I. Again, all I did just put I in the denominator. Believe me, those signs are really crucial. It looks like completely silly what I'm doing, but I wanna, I wanna take care of signs. Otherwise, we'll get garbage later. Okay, then I'm taking an integral. This is a simple ordinary integral, d2 sigma, square root of minus g, and then I have rho as a function of sigma. And then inside this integral, what I have an expectation value, the full quantum expectation value of nabla A, JA. Okay? So, what we did with you, we showed that if there is a symmetry transformation and we construct a current corresponding to this symmetry transformation, this current is conserved as an operator again. So from here, it follows that nabla A, JA equals to 0 as an operator statement. Right? Good. Everything is clear, right? Now we're going to derive a very important statement. And so, word identity. And once we derive it, I'm happy to call it quits because it's a good place to start. But don't let me lie. So let's see what happens. Okay. So what I'm going to do now, I'm going to repeat the same procedure on the blackboard by inserting additional operator. I want to write down some identity involving an operator. So what I have here, an operator A, which is inserted at sigma naught, right? So remember that rho of sigma has finite support. So you can think of this is that there is some region, and so inside this region, rho is not equal to 0, and rho equals to 0 outside. So now what I am studying, I'm studying one operator inside this region, inserted at point sigma naught. So sigma naught is inside support for inside support for rho of sigma. Right? Remember, rho of sigma was an arbitrary function that we choose. Now I'm asking the same question, so there will be some symmetry transformation. Well, if I have an operator, in general, the operator will transform as well, right? So A of sigma will go into A prime of sigma, which is A of sigma plus delta A. Okay, so there will be some transformation to the operator as well. And so what this means that when I do that, then there is a piece here, A naught, right? Sorry, there is A here. Then there is a piece here, A. And then there is an additional piece here, which is delta A of sigma naught. Okay, so is that clear up to now? All I said is that now I am studying the transformation. So here I have to put prime, right? And so Z prime is simply A plus delta A, and delta A is for the absolute, right? So I'm making infinitesimal transformation, and I'm keeping only linear terms. So there will be nothing, I mean, what we no transformation whatsoever. That's A of sigma. And then there are two pieces, one coming from transformation of the e to the minus s in the measure, and that gives the current here. But now it will be multiplied by A of sigma naught, right? And then there is additional piece when I don't transform anything here, and I just transform the operator itself. Okay? Clear? Good. So now you can see how important are my signs. Because now, when I'm making these manipulations, what I was doing, this zero, we have to recall what this zero is. So this zero was take this and subtract everything you have here, put it on this side, right? So, so what this tells me is that this zero will be minus delta A of sigma naught. And with my conventions, minus signs there as well. Okay? Simply because that delta A comes with a plus sign, and move it on that side, it will be minus. So what this tells me here is 0 equals minus delta A of sigma naught. And there is a plus sign there. And so now I have minus delta of A0 expectation value. Okay? Good. And so what we did with you, we actually derived an operator identity, this one. So this is known as a word identity for the field A, and we can. So is it clear? Is it clear what I did there? Important is a minus. So you agree with all my signs, right?
Sorry, but what is dividend?
Sorry?
What is dividend accurate here? I think there's another.
No, he agrees. He agrees. All right. Let's take this number.
Okay.
Yeah, is this a newer book? Well, there are again, it's okay, guys, because I really spend these conventions that we stick with is the ones that will lead to correct formulas later. You know, the possible disagreements could be the definition of the current there. I don't know. I will look. I will look at this. But for now, you can see that there is no, you know, I didn't fudge any signs. Okay. It's important it is really crucially important to me that there is a minus here compared to this piece. Yes. 3 minutes.
What happened to the A of sigma naught in the?
Oh, that's just canceled, right? Because this is just a change of variable. So this piece will cancel with this.
No, there's an A of sigma naught in the epsilon. Term.
There is no epsilon here in front of
No, in the epsilon term, the I epsilon over 2 pi. there's
Oh,
no
well,
A.
yeah. Okay, great. I forgot. This is really important. So this is a that's absolutely correct. So there is this is A of sigma naught. Yes, I forgot. That's an important piece. All right, very good. So now I have this as a integral equation, but I can write it down as an equation without the integral, right? So all I'm going to say is the following. So I'm going to say that nabla A, J A of sigma 0, right? So equals to, it's going to be equal to 1 over square root of minus G, delta function, sigma minus sigma naught, 2 pi over I epsilon delta A of sigma. Okay. So you can see that if I integrate both sides of this with the support, then I will get. Actually, I think that there is a sign. Okay, so what I did here, again, you can check that from here you can get this up to some sign, and you integrate, and the delta function will become 1. Yes. So let me write down one last formula, and then we'll call it quick. So I have this integral over the region R, which is so this region defined as rho of sigma is not equal to 0. So this was d to sigma square root of minus G nabla A G A of sigma naught, right? But I can write it down that my nabla acts on the product of two operators or two fields in this case, and so then this area integral becomes the integral over the boundary of the region, and A J A and then A of sigma naught. Okay, and so it must be equal to 2 pi over I epsilon delta A sigma naught. Right, guys. So we're gonna start next time with this, and I was a little bit fast at the end, so we'll sort out the signs next time. All right, guys. See you next week.